Okay, um, as I mentioned, we're going to move on from talking about the central limit theorem to talking about confidence intervals, and we'll start with estimating population means when you know the standard deviation of the population, which, as the book points out, get in the right window here, so come on. Oh, come on. There we go. All right, as the book points out, um, there we go, got the laser pointer. As the book points out, if we know the in order to know the standard deviation of the population, we have to have all the information of the population. So we wouldn't really need to estimate the mean. We could just plain calculate it. But as a building block in terms of building up to what to do when you don't know much about the population, it's a good starting point. Um, so let's just move on. So a major thing we try to do with statistics is provide information so that you can make decisions. Um, for example, networks may want to know how many Americans watch their TV shows each week. So you've got or at least there used to be the Nielsen ratings and things like that. Can't survey every single household, but they need the information so they know what shows are being watched and are what shows aren't, and they would cancel those and try something new, right? Um, so this is where inferential statistics, the branch of statistics that gets used to provide estimates for populations, that's where this comes into play. This really is where most of statistics, as we think of it and use it, sits right now. So for any particular parameter, there can be several statistics that can be used to find estimates. A point estimate is an estimate based basically on a single value. Um, so the best point estimate is one that's unbiased, and so it doesn't consistently underestimate or overestimate your population parameter. So ideally, it's comes very close to your population parameter. So there's some obvious things that can be used to estimate your population mean. Your sample mean is, of course, the most obvious. Sample median or sample mode. All those measures of the central tendency for your sample could be used to estimate the central tendency of your overall population. It doesn't necessarily, the sample modes and medians don't necessarily end up being centered about the population mean. We do know from the central limit theorem that the mean of a distribution of sample means, so if we made multiple samples and the average of the mean of that is the mean of the population if we arrange it so that the central limit theorem fits. So if we can do it for multiple points, the sample means, or the mean of the sample means becomes the best point estimate. So that the sample mean is probably our best unbiased estimator of the population mean. All right, so let's look at an example. So we've got some test scores on a standardized biology final exam. This is a random selection of test scores taken from the overall population. So we want to estimate the population mean based on these. So we will start with the sample mean as a good unbiased estimator. The sample mean for that particular population came to 81.6. X with the bar over it indicates that it's the sample mean. The Greek letter mu would be used for the population mean, of course. Okay. So our estimate for the population mean would be 81.6. Now, we're basing this just off of one measurement, in essence. So if you think about the central limit theorem, the more it was saying that if we broke this, what is this, 30? No, let's see. 1, 2, 3, 4, 5. Okay, so yeah, that's 30 samples. If we sampled, let's say it's a big lecture hall at a big university and there's 300 students in it. If we sampled in groups of 30 10 times, we'd have have that, and the central limit theorem would say that the average of the averages would be our population mean. But we've only got one value here, so we don't know if we've underestimated or overestimated. What we can do is calculate the likelihood that we're within some certain range of that of the actual underlying population mean. So we can give a range of values rather than just one. So that's an interval estimate. That's the range of possible values for the population parameter, and in this case the mean. We have the confidence level, or level of confidence. It's going to be denoted by C. It's the it's the it's the likelihood that the actual underlying population parameter lies in that range. So a confidence interval is an interval estimate associated with some confidence level. Most of the time, most statistics get reported in a 95% confidence level. That's fairly normal standard use. So you'll see 95% frequently. Other confidence intervals are possible, and we'll see some moving on. I did kind of misspeak. It's not a 95% chance that the parameter falls in the interval. The parameter is fixed. It's either in or not. We're 95% confident that that estimate matches it. It's some awkward phrasing down here. So we've got confidence intervals for the population mean from 10 random samples. So we've got our 10 random samples here, and these are the interval ranges for each of them. This is the actual value here. A 90% confidence interval, we would expect long term, as it says, 9 out of 10 would contain that the mean we're after. In this case, the fifth interval does not. So how do we come up with the confidence interval? How do we come up with it so that it means something? So really, it needs to be. We need to use the best point estimate we can find. So, right, we'll use the sample mean, and if we're estimating population mean. But the real question is, how big do we make that interval? So we come up with the margin of error. It's the largest possible distance that the this population parameter that let's stick with population mean instead of keeping it generic, will be from our sample mean. That it's easier to see and use. Let's go ahead to this slide. So we've got our margin of error, that's the term. We've got our margin of error here. If we subtract it, we get the lower bound. If we add it, we get the upper bound. That is our interval range, our confidence interval. And E is half of the value of the confidence interval. It's what we add and subtract. You might see this as with political polls, sometimes they report it as 40% plus or minus 2%. And this would be this E value is that 2% that's plus or minus. So let's look at this. So if we've got a college student researching study habits and collects data on 250 college students, calculates a sample mean of 15.7 hours per week, and the margin of error using a 95% confidence level comes to 0.6 hours. So what is the 95% confidence interval for her data? Go ahead and do that real quick. And we'll talk about the interpretation in a bit. But okay, so we've got 15.7 as the sample mean. That's our point estimate. Confidence interval is 0.6 hours. The endpoints are found by adding and subtracting that. So the lower section is our sample mean minus the margin of error, or comes to 15.1 hours. Our upper bound is sample mean plus that margin of error, so 16.3 hours. So our 90% confidence interval is between 15.1 and 16.3. We're 90% confident that the actual value falls within that range. So you can see as it gets broader, we're more confident. As it gets narrower, we're less confident. So we're 95% confident. I'm sorry, did I say 90? Sorry, I meant 95. I forgot which one we were using. 90% confident that students on campus, on average, spend 15.1 and 16 between 15.1 and 16.3 hours per week studying. All right, so if you're given the margin for error, this is pretty simple. You just add and subtract it. But if we don't have the margin for error, how do we calculate it? We've got to use the right distribution or some advanced statistical techniques. So in this case, we're starting with the sample standard deviation known. So you can keep it simple. If the central limit theorem applies, then we can use the standard normal distribution and the population standard deviation to help find that confidence interval. Right. So we're sticking to a simple random sample. Population standard deviation is known, and either the sample size is at least 30 or the underlying distribution is approximately normal. So the central limit theorem applies. That's the situation we're looking at right now. Okay, so the confidence interval corresponds to the area under the normal curve centered at our estimate. So you just sketch this. So yeah, they've got 95%. Okay, so we've got this. We've got a 95% boundary, and what we're trying to find is these z values that match the boundaries there. These are called the critical z values, and they are, as you can see, denoted by z sub alpha over 2. Um, alpha is, okay, they cover that in the next slide. Alpha is the kind of the additive inverse of the confidence interval or confidence level. Um, you know, remember we're on a scale of 0 to 100 here, so if we're 95% confident, our alpha is 5%. It's that leftover little bit. So alpha alpha represents these. There's my finger. These bits that are um, on the tail on either end, outside of that range. So there's going to be alpha over 2 on each end of that distribution. Um, so alpha over 2 equals the area in one tail. Z sub alpha over 2 would give you the area, the z-score associated with that area. Okay. The critical value is based only on the confidence level, not on the sample size or any population parameters. So the critical value is constant for any sample size. What it works out as after that can vary with sample size, but the critical values are pretty standard. So there is this nice handy dandy table on page 431 in your book that shows some of these confidence confidence levels and standard z-scores. So, like I said, 95% confidence level is a pretty standard one you see often. It's usually in scientific papers and such, if it's kind of the minimum that people are looking for in reporting their work. So the alpha associated with the 95% confidence level is 5%. The z-score associated with that is 1.96. You can see the z gets farther out as we gain more confidence, so we're expanding that. If then we're less confident, there's more chance that reality is outside of our sample in that case. Okay, so if we know the sample, sorry, if we know the population standard deviation, and we want to find the margin of error, we take the z-value associated with that margin of error, the critical z-value, and we multiply it by the population standard deviation, which is the sample standard deviation divided by the square root of the sample size. Pretty simple, pretty straightforward, as long as we know that. Okay. All right. So, as an example of this, if we wanted to estimate the average electric bill in a large urban area, we use using a simple random sample of 100 households, and we know somehow that the population standard deviation is 1550. We want to find the margin of error for a 99% confidence interval, rounded to 2 decimal places. So we're going to round to the nearest cent in this case. All right, so population standard deviation, confidence level, sample size. All right, do we have, no, we just want them, okay. All right, so we want to find the critical z values. So we'll go back to table 8.1. I can see that my critical z value is 2.575. Yep, there it is, 2.575. Population standard deviation is that. Sample size was that. Okay. So we can plug our values into that equation. Remember, this is critical z-score times the sample standard deviation. Sample standard deviation using the central limit theorem is population standard deviation divided by square root of sample size. Again, this is assuming that the population standard deviation is somehow known. And this gives us the area no, the critical z-score is associated with the area here under that portion of the curve. Okay, so margin of error comes to 3.99125 or $3.99 for the 99% confidence interval. Right, so the boundaries then are the sample mean minus the margin of error and the sample mean plus the margin of error. Right, E is our margin of error, X bar is the sample mean. Mu is the population mean. Okay, let's do another example where we know the sigma, the population standard deviation. So if we've got a new pseudo-sized hotline and we want to estimate how many calls to expect, randomly call 35 similar hotlines across the nation and find that those 35 hotlines average 42 calls per month. We want to create a 95% confidence interval for average number of calls per month. Assuming that we know the population standard deviation is about 6.5 calls per month. Oh, excuse me. All right. So step one, find our point estimate. We've got our sample mean of 42 calls per month. That is a pretty decent point estimate for our starting point. Next step is to find our margin of error. We want a 95% confidence interval. So we look at the handy-dandy table and we see that that is associated with critical z-score of 1.96. We've got our population standard deviation and our sample size. So we can go ahead and calculate it. Critical z-score times sample standard deviation, which should be 6.5 over the square root of 35. We get approximately 2.153453. Again, they've got this nice diagram that helps us remember what everything is. Our alpha value is 0.05, so 95%. Alpha is what's left over, or 5%, and then so that's half on each side, so it's 2.5% and 2.5%, and that's where the critical z-score comes from. All right, so to now calculate the actual interval, we will take our 42 call average, subtract off our margin of error to get our lower endpoint, and add on the margin of error to get our upper endpoint. and we'll have a range of 39.8 to 44.2. All right, next example, we have a toy company that we want to know the average number of new toys per child per year. So the marketing people collect data from 1,842 randomly selected children. We get an average of 4.7 toys per child. We want a 90% confidence interval for the mean. And somehow we know that the standard deviation for the population is 1.9 toys per child per year. All right, for the point estimate, we're going to be using the sample mean of 4.7 toys per child. Margin of error, we want a 90% confidence interval. So we get 1.645. 90% confidence interval, our alpha will be 10% then, right, 10%. So Z, the critical Z score is Z sub 0.05. Put our values into the formula. Critical Z score times sample standard deviation as estimated based on the central limit theorem. And we get 0.07282, so about 0.07 toys per child. So if we subtract our margin of error from that sample mean, we get 4.6 toys per child approximately. And if we add, we get approximately 4.8 toys per child. We can write it either of these ways. We're 95% confident that the true population mean is between 4.6 and 4.8 toys per child. All right, so if I've got a company producing hand-knitted socks for women, and I collect 431 randomly selected women's foot sizes, and I find that the average foot length for these 431 women is 8.72 inches. So I want a 95% confidence interval so I know how big to make my socks. Somehow I know that the population standard deviation is 0.36 inches. So here are the directions using the TI-8384. We're given the sample statistics. So we go in and we input things in the appropriate things. It uses the same notation. So we've got a 0.36 standard deviation, 8.72 sample mean, and 431 sample size. They want the confidence level in decimal form, so you should put it in like so. 0.36 with standard deviation, 8.72, 0.95, tell it to calculate. Oh, there it is. And the result should be spit out in that form, roughly, interval form. Alright, so we've got a study comparing the sensitivity of home AIDS tests to professionally administered AIDS tests using the same testing procedure. Measures of test sensitivity represent the percentages of results that are correctly labeled positive when HIV is actually present. Table shows the reported 95% confidence intervals for the sensitivity of both tests. Okay, so we've got our home test and our confidence the confidence interval is 86.6 to 96.9, and for the professionally administered test, it's 95.85 to 99.08. Okay, so keeping that information in mind, let's look at the questions about it. Which of these statements is the most unbiased interpretation of those results? First option, the professional tests were far more reliable with 99.08% sensitivity, and the home tests were only at 86.6%. Let me go back to see what was what. We've got, that one is reporting the lower boundary of the home test and the upper boundary of the professional test. Home testing methods for HIV are just as sensitive as those administered professionally. They are even more sensitive since they have 96.9% sensitivity compared with 95.85 for the professional ones. So let's go back and look. So yeah, we're comparing the high bound for the home test with the low bound for the professional test. Then the last option is the results provide reasonable assurance that the home test is as effective as the professional test. So we're not comparing either. We're just pointing out that it's reasonably similar. So as they point out here, the confidence intervals overlap. It is possible that both tests have the same sensitivity rating, which is a reasonable assurance that they are similarly accurate. This is actually the findings as reported to the FDA. Option 1 doesn't give a fair picture of the results because you're cherry picking the highest result in one, the lowest result in the other. It doesn't reflect the real possibility that the sensitivity ratings did not differ. Option 2, it's the same thing, just in the opposite direction. All right, so next thing is really the question here is how small a sample can we get away with and still have some meaningful results? Sampling can be a fairly expensive thing, either scientifically or surveys, whatnot. It can be, the more data you have, the longer it takes, the more people you have to talk to, the more time it takes, the more money it costs. So, what's the minimum sample size is an important thing to know. Ideally you want as much data as you could possibly get because your numbers will be better. They just will. But at the same time, you want to spend as little as you can. So, what's the least you can get away with and be reasonable, and then get as much more as you can. So if you're using more data, it increases the level of confidence without increasing the margin of error. So how large a sample size do you need for any particular margin of error? Okay, well, we can rearrange the formula for margin of error. Again, this is the formula as based on the central limit theorem, because we've got our sample population and our standard deviation. You remember that was the you were dividing by the square root of that, so we rearranged things. You're dividing at one point by the square root of the population, sample population. So we've rearranged it and squared it so that it's the sample size is equal to that. So if we want a specific margin of error and we want a specific confidence interval, we can calculate what the sample size has to be to match that. Ah. Okay. Okay, so we need, this is upfront in the planning stage, so we need some way to estimate our population standard deviation before we know anything. One method is to use the sample standard deviation as a point estimate for that. Or we can try to match a similar study. Now, if we're trying to figure out what the sample size is, we probably don't know the sample standard deviation yet. If we know the range of the population, we can divide that by 6 and use that as a nice starting estimate. The thing to remember is that we are trying to determine a number of data points we need. And that's going to be a whole number. I can't have half a data point. So if we end up with something that's not a whole number, round up. And you should always try to get as many data points as you possibly can. This tells us what the minimum we have to have is, though. All right, so for example, if we want to be 90% confident that a sample mean is within 2 units of population mean, and we've got an estimated population standard deviation based on a previous study, what's our minimum sample size given that? Oh, there you go. All right, so we've got a 90% confidence interval and 8.4 as an estimated standard deviation within 2 units, so margin of error should be 2. We want a 90% confidence interval, so we can look at the table of critical z-values and find our z-value associated with that is 1.645. We can plug those into our formula and we get 47.73 or 48 is our minimum number of samples. Okay.